Dust is everywhere, mainly in people's living rooms, but also in space. About 1% of the interstellar medium, which is the material between the stars, is dust. And most of this dust is made in dying stars. But how does the stardust make its way to our labs? And which exciting stories does it have to tell us? The gas and dust that is thrown out into space from dying stars can reaccumulate and give birth to a new stellar system, as it did for our solar system 4.6 billion years ago. Most of the dust was vaporized in the young solar nebula with temperatures of around 1000 Kelvin, and therefore the elements that were carried within the dust were well mixed, like the ingredients of this muffin dough. Still today we observe this averaged elemental abundance in the oldest meteorites that formed during the cooling of our solar nebula, and we also observe it in the spectrum of our solar photosphere. But some tiny particles of just a few micrometers in size manage to survive the harsh temperatures of our solar system. These particles are known as stardust, or pre-solar grains. During the formation of our solar system, they became trapped in meteoroids. Like these chocolate chips, which are protected by the surrounding dough, the stardust grains were shielded by the meteoroid material from the outside hazards that would alter the grains, such as cosmic radiation that can change their composition. Safely stored in their time capsule, the stardust remained preserved for 4.6 billion years. See that shooting star? If we are lucky, the meteor has the appropriate size to survive the atmospheric entry and bring the stardust directly to us. Oh, I'm lucky! The stardust grains are extracted with strong acids that dissolve most of the meteorite, but not the stardust. And they are detected in situ with imaging methods. The tiny grains are made of silicon carbide, silicates or graphite. About 10,000 stardust grains in a row make the size of a chocolate chip. But most of the stardust is composed of even 1,000 times smaller nanodiamonds. The stardust grains derive from different stellar sources, and the composition of individual grains can give information on the star itself. They are analyzed with mass spectrometry methods, which commonly are fatal for the stardust grains. Yes, scientists don't even spare the diamonds, as they are either vaporized or thermally ionized or bombarded by ions and sputtered away. Ha! And another one bites the dust. Compared to the averaged composition of our solar system that results from mixing in the young solar nebula, stardust grains show anomalies. These anomalies are fingerprints of the nucleosynthesis processes in the stellar type the grain was born in. For instance, the predominance of carbon-13, the heavy type of carbon measured in some silicon carbide grains, is typical for the atmospheres of red giant stars or novae. And the presence of radioactive isotopes of titanium in other grains points to their formation in the remnant of an exploding star, a supernova. This also means that these grains enable us to learn more about nucleosynthesis and mixing of elements in their parent stars. When did these stars die and release the freshly formed dust? Well, some grains are up to 7 billion years old. That means they floated around in interstellar space for up to 2.4 billion years before being built into our solar system. They are the oldest material that we can analyze in the lab, even older than our Sun. and that's why stardust is also called pre-solar grains. But dating is a difficult task. Pre-solar grains cannot be dated with astronomical methods, and dating with radioactive isotopes, similar to the radiocarbon dating method, does not work because the grains are so tiny and therefore the decay rate from the few radioactive isotopes is extremely low. Therefore, another method is used. When stardust grains float through the interstellar medium, they are constantly bombarded by cosmic ray particles, such as highly energetic protons and helium nuclei. These particles induce nuclear reactions that form new isotopes that slowly build up with time. By measuring the amount of those isotopes, the so-called cosmic ray exposure age can be determined, which gives us an estimate on how long these grains were traveling through space before they became trapped in the meteorites and were shielded from the cosmic rays. Comparatively young stardust from supernova explosions that happened close to our Earth in the past millions of years was found deep down at the ocean floor of our Earth. Hear more about this in the next video of Astronuclear Nibbles.